So a 3 kilogram box is being dragged along the floor to the right by a horizontal rope. The force exerted on the rope varies over time according to this particular equation, which is in newtons, and T is in seconds. A friction force of 1 newton acts in the direction opposite the motion. So we've got two parts to answer. The first one is to draw a complete free body diagram of the box, and the second one is going to be to use that free body diagram to apply Newton's second law of motion and solve for the first order ordinary differential equation relating the box's velocity and time. Alright, so let's start by drawing our free body diagram. So if we're drawing a free body diagram of just the box, that means we need to isolate it from the ground. Okay, so it's free of the ground, which means that the ground should not be pictured in this free body diagram. Alright, so we have a few different forces that we need to apply onto the box. So the first one that's pretty obvious, I think, is the one where we have this applied force through the rope. So applying that onto the box, it's going to be to the right. It's been called F applied, and if we want to, we could replace it with this mathematical representation that we're given up in the question. Alright, so that's our applied force. The next thing I might consider is the fact that we know this box has a weight associated with it. So we know it's 3 kilograms, and if I apply that weight, it's going to be through the center of gravity, which I'll assume is at the middle here, and it's going to be equal to mg, so that mass times gravity. So that's going to be 3 times the 9.8, and this is equivalent to 29.4 in newtons. Alright, so the next thing I'm going to consider is the fact that this box is contacting against this surface, the floor or whatever it is. So what that means is we're going to have a normal force or a contact force between them. And we know that the contact force, or the normal force, acts perpendicular to this contacting surface. So that means it's going to act straight back up. Okay, and I'm going to call it N for normal. The very last force that we have to consider is the fact that we're told that friction is acting in this scenario. And we're told that friction is going to act in the direction opposite the motion. So I'm assuming that this box is going to move to the right, and I mean it kind of tells us that up here in the question. So I'm going to draw it in a different color because this isn't a force, so it's not technically part of our free body diagram. But what this is telling me is I'm assuming that the velocity is going to the right. So if the friction force is going to oppose that, it means it's going to have to go back to the left in the opposite direction. So this is going to be F friction, and we're told that that is going to be 1 Newton up here in the question. Pop in here as well. Alrighty, so that's all there is in terms of drawing that free body diagram. Picked up all the forces that we possibly are considering. So now we're up to part B, which is looking at applying Newton's second law of motion for the first order ODE relating the box and the velocity over time. So let's scoot this down a little bit. So Newton's second law is the one where sum of the forces have to equal mass times acceleration. Now, I'm going to only really need to look in the horizontal direction here in order to pick out what's happening in terms of the motion. That's because the block itself is only able to slide in that direction. It's not going to be able to move up or down in this scenario. Alright, so what I'm going to write this out is sum of forces in the x direction is going to equal the mass times acceleration in the x direction. And you could do it in the y direction, but really all you're going to find is that the normal force is equivalent to the weight force. Alright, so let's go ahead and do this. So forces in the x direction. I've got my friction force here, and I'm going to assume that if I pop in my coordinate system, this is in the negative x direction, so I'm going to pop it in my equation as -1. And the only other force in the horizontal direction is this applied force, and it's in the direction of the positive x-axis, so it's going to go in as positive to my equation. Alright, so it's equal to the mass, which I'll just leave as m for the moment, multiplied by the acceleration in the x direction. Now we're assuming that this block is going to move to the right, alright, as written here with my velocity. If I wanted to, I could also pop in a for the acceleration. I'm assuming it's going to accelerate that way. So that means when I pop it in the equation here, a should go in as a positive value because it's going to the right. Alright, so that is my equation. So I should be able to simplify this a little bit on the left hand side. The -1 and the 4 can go together to make 3. And at this point I'm going to sub in the mass. So we were told that it's a 3 kilogram box. So we can pop this in as 3 and A for the acceleration in the x direction. Alright, so one more thing I can do is probably if I divide everything by 3, it's going to make my equation a little bit nicer. We get that. Right, so at the moment what we have is an equation that relates together the acceleration of our block to the time t. Now if we scroll back up, what we were looking for is a differential equation that related the box's velocity and time. So velocity is the key word here. So what we need to do is change this over from acceleration into velocity. And what we know that these are related, we know that acceleration is the rate of change of velocity over time. So we can go back and substitute this in. So we're going to get the left hand side staying the same, but the right hand side here, I'm going to change it over to be dv dt for the rate of velocity over time. Now we can really see that this is definitely a ordinary differential equation because we have a differential part in here, and we can see that it's first order, okay, because it's just the first derivative of velocity with respect to time. And that's exactly what we were asked for back up in the question. It was a first order ordinary differential equation relating the box's velocity and time. So this is the answer to that question. So that's pretty much all there is for the video.